Very good morning to everyone. Myself Juli Yadav, Assistant Professor in Computer Science and Engineering Department from Akgec Engineering College, Ghaziabad. So my today's topic of presentation is hill climbing algorithm. Basically, this algorithm we are going to study in artificial intelligence. Why we are studying this algorithm? Because artificial intelligence contains so many techniques for searching. What does it mean? It means that when basically what we do in artificial intelligence, we are creating an object, an artificial object that has the same intelligence as the humans have, right? So while it perform or it proceeds for taking the actions, it need to do searching, right? That searching is based on various algorithms or various techniques are used for finding the solution to any appropriate or any particular problem. So to find the solution, we are having so many techniques like informed search, uninformed search, local search. Informed search contains so many techniques like A star, BFS. The BFS is best for search, and in uninformed search technique we are going to study about DFS, depth first search, breadth first search, uniform cost search, iterative deepening, depth first search, depth limit search, bidirectional search, and many more. And this algorithm is basically the local search algorithm that we are going to use in artificial intelligence. So let us take a look what is hill climbing algorithm. First thing is that it is a local search algorithm. So basically a hill climbing algorithm is a local search algorithm that continuously moves in a direction of increasing evaluation or value to the peak of the mountain or the best solution to the problem. Basically, when there is a condition in front of the artificial object that has the same intelligence as the humans have, right? When it has some problem, it need to find the solution, and when the solution is finding on the basis of hill climbing algorithm, which means it is a local search algorithm that find the solution in an increasing order. Like if this is our problem, then to find the solution of this problem, the solution can be found, means there are various, for example, in a mathematical equation we are computing something, right? To find the appropriate or the efficient answer, we are moving in an increasing order. As the increasing order has some value, like here is some value, here is some value, here is some value. This what does it shows? It shows that this value is better than the previous one, right? In the same way, this value is better than the previous one. If let us consider it is x1, this is x2, and this one is x3, and here it is x0. So suppose these are the solutions for any particular problem. So to find the best solution or to find the optimal solution, we are having 4 solutions, which indicates that x0 is the solution, x1 is the solution, x2 is the solution, x3 is the solution. But here, to find the best solution or to find the appropriate or efficient solution, we are comparing the value. We are comparing the value or we are comparing the solution value of the solution, right? Here you can see the value of x. When we are here, when we are at the x0, we find it is the best value, right? But we need the best value. We are moving in a upward direction, in an increasing order, right? Here it shows that x1 has the better solution, or x1 is the better solution in comparison to x0, which in further when we are moving up, we find another value, that is x2, which is better than the previous value x1. Then x3, which is better solution or better value in comparison to x2. So we are moving in an increasing value or increasing order to find the peak of the mountain. Peak of the mountain indicates the best solution. If the problem has the best solution is x3, then it is the peak value, means beyond this it goes in a decreasing order. So we considered it as the best solution, and this is what the peak of the mountain is. Peak of the mountain contains the best value. So, x3 is the best solution to any particular problem, right? When does it terminates? It terminates when it reaches a peak value where no neighbor has the same value or the higher value. Means if we are reaching here x3 is the value, and we want to find the more best solution or more appropriate, and when we are moving we find a drop down, or we find the values in a decreasing order. So, we feel that here it is terminated. Why? Because when it reaches a peak value where no neighbors has a higher value, means if x3 is the highest value and x2 is the lowest value is in comparison to x3, but x3 is the highest value, no other values are greater than the x3, then we consider it as the peak value. We consider it as the peak value, and this is the way, this is the point where the algorithm terminates. Basically, it terminates where the neighboring value has, the neighbors do not have the higher value than the particular value. So, basically, hill climbing algorithm is a technique in which it is used for optimizing the mathematical problem. The basic, or we can say the implementation or the practical application of hill climbing algorithm is in mathematical problem. One of the widely discussed example of hill climbing algorithm is traveling salesman problem. Traveling salesman problem is the highest, or we can say the most discussed problem that can be solved using the hill climbing algorithm. What we do in hill climbing algorithm, in which we need to minimize the distance traveled by the salesmen. What the TSP problem does, in TSP problem, when we are giving a set of cities that are connected with each other, the problem is we need to travel each and every cities, if we are starting from A, and if there are 5 cities, then the salesman has to start from A and it has to travel to all the cities that are connected with the A, right, and it stop its searching at A. So, the traveling considered the distance, right? If we are traveling from A to B, then it has some distance. If we are traveling from B to C, then it has some distance. So, traveling salesman problem indicates which has the minimum distance. If the traveling salesman person travels all the cities in which it needs to be traveled with the minimum distance, then that problem is TSP problem, which can be solved by using the hill climbing algorithm. So, we generally used to call this algorithm as the local search algorithm, but sometime we can also say it as the greedy local search algorithm. Why we are saying it as a greedy? Because it looks, or it considers only the good immediate neighbor state, not beyond that. What does it means? If this is the value, this is the peak value, beyond this all the values are lower than this value, and there is no other value that are higher than this value, right? Then this is the best solution or the good solution, right? So, it only considered about a good immediate neighbor state. Like if we are here, then the better solution is greater than this value, right, which is the good solution, or we can say it is the, if this is neighbor, then this neighbor has the better neighbor, or the immediate neighbor that has the better value is the output of, or the solution for that particular problem. That's why we are saying this this algorithm is also known as the greedy local search algorithm. So, basically a node of hill climbing algorithm has two components, which are state and value. State and value. Now, what does this state and what does this value is? State. Let us suppose considering a traveling salesman problem, here are 4 cities A, B, C, D, right? If this is the problem of traveling salesman problem. There are 4 cities A, B, C, D. 4 cities and all are connected with each other, right? All the cities are connected with each other. If the distance from A to B is 2 kilometer, distance from B to C is 3 kilometer, distance from C to D is 5 kilometer, distance from A to D is 2 kilometer. The person has to travel to all the cities with the minimum distance. If A travels from A to B, if a person travels, salesman travels from A to B with 2 kilometer distance, and now B has to reach to D. Starting from B, if it reaches 2 kilometer, it takes 2 kilometer to reach to D, and it takes 2 kilometer to reach from A to C, right? Then how we can find then which value is the better value, which is the solution for this TSP problem. Now let us see, traveling from A to B. If we are traveling from A to B, these are basically the states, like A states, B state, C state, D state. These are the states and they have some values that are 2 kilometer, 3 kilometer, right? These are the values. Now, if we travel from A to B, it takes 2 kilometer. If we travel from B to C, it takes 3 kilometer. If we travel from C to D, it takes 5 kilometer. If D to A, it takes 2 kilometer. So the value is 2 plus 3, 5 plus 2, it is 12 kilometer. If the salesman wants to travel the whole the cities with A to B, C, D and again A, then it takes 12 kilometer. Let us see, is there any other solution also available? If the salesman starts traveling from A to C, A to C, A to C with 2 kilometer plus C to D is 5 kilometer, then C to B is 2 kilometer and B to A is 2 kilometer. Now we can see that the salesman can reach from A to B to C, D as well with the cost of 2 plus 5, 7, 8, 9, 10, 11. So 11 means a salesman can travel all the 4 cities with the value of 2, that is one is 12 kilometer, another one is 11 kilometer. So the motive of TSP problem is traveling all the cities with the minimum value, and the minimum value among them is the 11 kilometer. So this is the states, these are the states and the values, right? So hill climbing, it generally or mostly in every case it's give a good heuristic value that is available in the problem or in the solution. So every time it gives a good or the good heuristic solution that is available in the solution set. So in this algorithm we need to maintain and handle the search tree or graph as it only keeps a single current state. The when we are searching the solution, right, when we are searching the solution in an increasing order, we are searching the solution in an increasing order. During the search, it only considers the current state. It does not consider the previous state. While it is comparing, while it compares the solution of previous state with current state, then it finds it the best solution. Now, this state and this state need to be compared, and this is the best solution. In the same way, this is the best solution. Oh, so it consider or keeps only the single current state. So this is the solution for that particular problem. So it has some features like the main features of a hill climbing algorithm is generate and test. What does it mean? What does it mean? Whatever it generates, like if this is the solution, here it is here it is x0, x1, here it is x1, here it is x2, and here it is x3, right? It generate and test variants. What does it mean? It means while it generates a solution, if it generates a solution x0, it generate, using this solution it generates the next solution. Now it tests whether this solution is best or the previous solution is best. So that is why this algorithm is known as generate and test variant. It generates the value or it generates the solution as well as it tests the solution that has been generated. So in a hill climbing algorithm is the variant of generate and test method. The generate and test method produce feedback which helps to decide which direction in which direction we need to move, or in which direction the state space diagram need to be explored, right? It also provides that, right? If this is the best solution, means there is no other solution present in this state space diagram, then we can say that this is the best solution, right? So that is why this algorithm is known as, or it has the features of generating the solution as well as it also test the variants. It is also known as the greedy approach. I have already told you why it is a greedy approach, because it's find or it tries to find the solution in a better or in a best way. It only considers the best value, right? So hill climbing algorithm search moves in the direction which optimizes the cost, either in terms of cost, in terms of efficiency. It just maximizes whatever it is, either cost or efficiency. That's why it is a greedy approach. One more thing, there is no backtracking. What does it mean? Means if we are finding the solution, in a particular direction, if we have reached here, then this algorithm does not have the feature of backtracking. Means if this we have reached here, then we cannot go in a backward direction. That is why no backtracking is available in hill climbing algorithm, because it does not. Why there is no backtracking? Because it does not consider or it does not remember or contains the value of the previous state. That's why there is no backtracking. So let us understand the state space diagram of hill climbing algorithm. What does a state space diagram? It is basically a graphical representation of hill climbing algorithm which shows a graph between various states of algorithm and finding the best objective or the cost. So it is a graphical representation of various states along with the object or their cost. So on the x-axis we have taken the function which can be an objective function or a cost function. So in a state space diagram, on the x-axis we are considering either the objective function or the cost function, right? And if the function on y-axis is cost, then the goal of search is to find the global minimum and global maxima. If we are considering y as the cost factor or y-axis as the cost or the objective function, then we need to find the global minimum and local minimum value, right? Then and the state space or the states are representing on the y-axis. So x-axis, y-axis contains the cost function or the objective function, and the x-axis contains the states, whatever the states are present in that particular state space diagram, right? And while we are considering the y-axis is objective function, when we are considering it is cost, then we need to find the global minimum and local minimum. Why the y-axis contain objective function? Then we need to find the global maximum and local maximum, because objective function varies according to the solution. So here it represent y-axis represent objective function and x-axis represent the states. These are the states. So this graph represents the state space diagram of hill climbing algorithm, which contains the following terms like shoulder. I will explain you later what the shoulder means. Global maximum, local maximum, flat, and the current state. So these are the points that, or the terms that need to be understand while we are going to study about the state space diagram of hill climbing algorithm. So let us have a look on what the terms are. So first is local maximum. Local maximum is the state in which which is better than its neighboring state, but there is also another state which is higher than that it. So here you can see this is the state space diagram. This point is considered as local maximum. Why? Because if we are on this current state and we are searching and finding the best solution, and when we reach here we did not find any neighbor has the highest value than this, so we considered it as the local maxima. Why it is local maxima? Because if there is a possibility of backtracking, if there is a need of backtrack, if there is a feature of backtracking available, then we can find it represent that this is not actually the good solution. Why? Because there is also a solution available in the state space which is better than or the best than this, right? That is why this is known as the local maximum. Means the solution that we have find is not the appropriate or the best solution. Another solution that is better than this solution is also available in the state space diagram, which is called as the global maximum. And then current state. It is a state in which a landscape diagram where an agent currently represent. The current states represent which state needs to be compared with the other state, or the solution of which state needs to be compared with the other state solution. Then flat local maxima. It is a flat space in which the landscape where all the neighboring states of the current states have the same value. So this is the flat space. What it represents? That if we are here, then this, these all the neighboring values are the same. That is why this is known as the flat surface or local maxima, right? Then what is shoulder? It is a plateau region which has an uphill edge. This is a this represents the flat, right? But when there is a uphill in the state space diagram, then we call it as shoulder, not flat. Flat is this which has a downfall after some time, or which has a downfall after finding the solution of some states. But if we consider the same flat, but if there is a uphill, then we call it as the shoulder. So few more terms I will explain it to you later. We will going to study about different kinds of hill climbing algorithm in my next video lecture. Thank you so much.